This is page AP1-1, problem number 6. Part A, I want to find the values of A and B such that the function is continuous everywhere. The places I'm concerned about are at x is equal to 2 and 5. I want it to be continuous at those places. So what that means is that, for example, for at x is equal to 2, I need the limit as x approaches 2 from the left. Now this is the left portion because these are the numbers less than 2, so this is the part of the graph to the left of 2. So this is ax squared plus x minus b needs to be the same as the limit as x approaches 2 from the right, which is the ax plus b part. That's this part right here because these numbers are bigger than 2. And I'm going to plug the 2 in for the x's. So this would become 4a plus 2 minus b is equal to 2a plus b, plugging the 2's in for the x's. I'm going to go ahead and rearrange this equation and put the a's and b's on the left. So I'm going to subtract this 2a over to the left. 4a minus 2a is 2a. I'm going to subtract this b over to the left. Negative b minus b is negative 2b. And I'm going to subtract this 2 over to the right, and that would be negative 2. And I think I'll go ahead and divide everything by 2. A minus b is equal to negative 1. But I still don't know what a and b are. So I'm going to repeat the process and do this same process at 5. So I need the limit as x approaches 5 from the left. These are the numbers to the left of 5, so I'm using the ax plus b part. Needs to be the same as the limit as x approaches 5 from the right, which is the last section of the graph. And I'm going to plug the 5's in for the x's, and this would become 5x plus, 5a. I'm plugging it in for the x, so this would be 5a plus b and 10a minus 7. And I will subtract 10a from both sides and get negative 5a plus b is equal to negative 7. So now I have a system of equations. I have this equation and this equation, 2 variables, 2 equations, so I'm going to solve the system. A minus b is equal to negative 1, and I take the other equation, negative 5a plus b is equal to negative 7. It's already set up so that the b's eliminate. And I have negative 4a is equal to negative 8. So a is equal to 2. Plugging the 2 back in here, I have 2 minus b is equal to negative 1. Negative b is equal to negative 3. b is equal to 3. Always write a conclusion. So, therefore, when a is equal to 2 and b is equal to 3, f is continuous everywhere. So, I'm going to write up here at the top what our new function is. F of x is equal to, remember a is 2, so this would be 2x squared minus x, and b was 3, so minus 3. That's when x is less than or equal to 2. This one is 2x plus 3 when x is between 2 and 5. And this is 2 times a. 2 times 2 is 4x minus 7. When x is greater than or equal to 5. So that's that's the function that's continuous everywhere, plugging the a and the b in. So now we're ready for part B. Part B is to evaluate the limit as x approaches 3 of this new function that we wrote up here. Now 3 falls in this middle section because 3 falls between 2 and 5. So this is basically asking me to find the limit as x approaches 3 of 2x plus 5. I'll plug the 3 in for the 2, and I will get 6 plus 5, which is 11. That's all there is to part B. Part C, I want to find, first of all, I need to get that function f of x over x minus 1, and this got cut off. This is as x approaches 1. So this is the part of the graph that I'm concerned about. So for part C, I want g of x is equal to the f of x part that we care about, which is this part, over x minus 1. And I want to find the limit as x approaches 1 of this. And if I plug a 1 in for x, I will get I see I made a mistake. This should be plus right here. Plus, plus, plus. Okay, so now when I plug a 1 in, I would get 0 over 0, which would be indeterminate. So take action. And one of the actions I can take is factoring. So I will factor the numerator. And reduce, and then plug the 1 in for x, and I get 2 plus 3 is 5. And that's part C.